Hello, and this is Cracking the AP Environmental Science Exam 2018 edition. Chapter 4, Earth's Interdependent Systems. In this chapter, we will discuss planet Earth's structure and its resources. This review will act as a foundation for many of the chapters that come after it, so pay close attention. According to the College Board, about 10 to 15% of the test will be on the material that's contained in this chapter. So consult your textbook for more information about subjects that don't look familiar. We will begin by discussing the components of the solid Earth, what it's made up of, how long it has existed, why we have earthquakes and volcanoes, and things like that. This will be followed by a discussion of soil, how it is formed, what it's composed of, and why it's important to humans. We'll move on to discuss the atmosphere, its structure, and how it produces the weather we experience. The atmosphere, hydrosphere, and biosphere are all intrinsically related and can almost not be discussed separately. However, we've broken them down into neat sections for review, and we'll go through everything you'll need to know about these systems for the test day. We'll end this chapter by reviewing oceans and freshwater bodies. We'll refresh your memory about certain environmental issues that pertain to Earth's water supply too. Welcome to Planet Earth. The first thing you should know about Earth is its history. Earth is thought to be between 4.5 and 4.8 billion years old. The amount of time is pretty inconceivable to humans, but the geologic timescale on the following page will help you get a sense of the vast amount of time that has gone by since Earth was formed. You will not be responsible for memorizing all the eons, eras, periods, and epochs for this exam, but you should be familiar with the major ones. They will come in handy. Where is Earth in the solar system? Earth is the third planet from the Sun in our solar system, which contains a total of 8 planets. From the Sun outward, the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. You probably already know that Earth and the other planets orbit the Sun in an elliptical pattern. And of course, it takes Earth about 365 1/4 days or 1 year to complete its orbit of the Sun. What is Earth made of? Planet Earth is made up of 3 concentric zones of rocks that are either solid or liquid, molten. The innermost zone is the core. The core has 2 parts, a solid inner core and a molten outer core. The inner core is composed mostly of nickel and iron, and is solid due to tremendous pressure. The outer core is composed mostly of iron and sulfur, and is semi-solid due to low pressure. Surrounding the outer core is the mantle, which is made mostly of solid rock. The mantle has an area called the asthenosphere, which is slowly flowing rock. The lithosphere, a thin rigid layer of rock, is the outermost layer of the Earth. The lithosphere contains the rigid upper mantle and the crust, the solid surface of Earth. Tectonic plates. Because the lithosphere floats atop the asthenosphere like a cracker on a layer of hot pudding, it can move and break into large pieces or tectonic plates. There's a total of a dozen or so tectonic plates in the lithosphere that move independently of one another. The plates are made up of both mantle and crust. The majority of the land on Earth sits above 6 giant plates. The remainder of the plates lie under the ocean as well as the continents. Some plates consist only of ocean floors, such as the Nazca Plate, which lies off the west coast of South America, while others contain both continental and oceanic materials. One example of the latter is the North American Plate, where the United States is located. This plate extends out to the mid-Atlantic ridge. There is even a plate that is located exclusively within the Asian continent. Its boundaries nearly coincide with those of Turkey. The largest plate is the Pacific Plate. It primarily consists of ocean floor, but it also includes Mexico's Baja Peninsula and southwestern California. The major plates of Earth are shown on the map below. The edges of the plates are called plate boundaries, and the places where plates are abut each other is where events like seafloor spreading and most volcanoes and earthquakes occur. There are 3 types of plate boundary interactions. Conversion boundary. 2 plates are pushed toward each other. One of the plates will be pushed deep into the mantle. Diversion boundary. 2 plates are moving away from each other. This causes a gap that can be filled with magma, and when it's cooled, new crust is formed. Transform fault boundary. Two plates slide from side to side relative to each other, like when you rub your hands back and forth. These are called transform boundaries. So what happens when plates collide? It depends on what types of plates collide and where. Converging ocean, and converging ocean-continent boundaries often result in subduction, in which a heavy ocean plate is pushed below the other plate and melts as it encounters the hot mantle. Converging continent-continent boundaries result in the uplifting of plates to form large mountain chains, like the Himalayas, which were created by a collision between the plate carrying India and the Asian plate, the Urals, the Alps, and the Appalachian Mountains. One important result of plate movement is the creation of volcanoes and earthquakes. Let's examine those next. Volcanoes and earthquakes. Volcanoes are mountains formed by magma from Earth's interior. Active volcanoes are those that are currently erupting or have erupted within recorded history, while dormant volcanoes have not been known to erupt. It's thought that extinct volcanoes will never erupt again. Volcanoes form where tectonic plates meet. At these junctures, breaks occur in Earth's crust and magma flows out. If no outlet is available as the plates push together, pressure builds up until it is relieved in an explosion, a volcanic eruption. Active volcanoes are categorized by the kind of tectonic event that produces them. They are associated with the following. Rift valleys occur when plates move away from each other. New ocean floors formed as magma fills in where the plates have separated. Magma rising from rift valleys is basaltic. It is thick and forms pillow lava upon touching the cold ocean floor or water. Subduction zones occur where plates collide and the denser plate, oceanic, subducts beneath the less dense continental plate. Hotspots do not form at the margin of plates. Instead, they are found over hotspots, which are areas where magma can rise to the surface through the plates. The Hawaiian Islands are thought to have formed over a hotspot. The magma is often basaltic, but it can also be rhyolithic, which is generally associated with continental hotspots. There are three types of volcanoes. Shield volcanoes have a broad base and gentle slope. They generally form over ocean hotspots and usually have mild eruptions with slow lava flows. Sometimes, however, when water enters the vent, they be very explosive. That's the book's words, forming pyroclastic flows, a fluidized mixture of hot ash and rock. Composite volcanoes have a broad base but steeper slopes. They are formed at subduction zones and are associated with violent eruptions that eject lava, water, and gases as superheated ash and stones. Cinder volcanoes form when molten lava erupts and quickly cools in the air, hardening into rocks that fracture as it hits Earth's surface. Cinders. They are small and generally form near other types of volcanoes. Earthquakes as the result of vibration, often due to sudden plate movements deep in the earth that release energy. Earth's tectonic plates move slowly all the time, at about the same pace as fingernail growth. But earthquakes are very sudden movements. They often occur as two plates slide past one another at a transform boundary. The focus of the earthquake is the location at which it begins within the earth, and the initial surface location is the epicenter. The size or magnitude of earthquakes is measured by using an instrument known as a seismograph, which was devised by Charles Richter in 1935. The Richter scale measures the amplitude of the highest S wave of an earthquake. Each increase in Richter numbers corresponds to an increase of approximately 33 times the energy of the previous number. In January 2010, an earthquake of the magnitude 7.0 struck the nation of Haiti. The center of the quake occurred in the boundary region separating the Caribbean plate and the North American plate. Officials estimate from the U.S. Geological Service had 222,570 people killed, 300,000 injured, 1.3 million displaced, 97,294 houses destroyed, and 188,383 damaged across the Port-au-Prince area and much of southern Haiti. This includes at least 4 people killed by a local tsunami in the Petite Paradis Island near Léogâne. Tsunamis are very large waves, or chains of waves, caused by movements of the earth during an earthquake or volcanic eruption, and can be extremely destructive. In March 2010, Japan suffered an earthquake of 9.0 magnitude off the eastern coast near Sendai. This quake caused a massive tsunami wave that was 33 feet high. Both the earthquake and tsunamis caused extensive damage. Many buildings, roads, and railways were destroyed. Major fires occurred. Villages, thousands of homes, and people were washed away, and at least 3 nuclear power plants experienced dangerous explosions. The rock cycle. Rocks are all around us, in the soil, our buildings, and or used in the industry. So where do all those rocks come from? The answer is other rocks. The oldest rocks on Earth are 3.8 billion years old, while others are only a few million years old instead. This means that rocks have to be recycled. The process that does this is the rock cycle. In the rock cycle, time, pressure, and the Earth's heat interact to create 3 basic types of rocks. Igneous rocks result when rock is melted by heat and pressure below the crust into a liquid and then re-solidifies. The molten rock, magma, comes to the surface of the earth, and when it emerges, it is called lava. Solid lava is igneous rock. An example of an igneous rock is basalt. Sedimentary rocks are formed as sediment, eroded rocks, and the remains of plants and animals build up and is compressed. Sedimentary rocks form under the water as sediments or dissolved mineral deposits on a stream bed or ocean floor. They are compressed as more material is deposited and then cemented together. As an example of a sedimentary rock is limestone. Metamorphic rock is formed as a great deal of pressure and heat is applied to the rock. This can happen as sedimentary rocks sink deeper into the earth and are heated by higher temperatures in the earth's mantle. An example of a metamorphic rock is slate. It is a product of the metamorphosis of shale. The diagram on the next page illustrates the rock cycle. Make sure you are familiar with it before the exam. Soil. One very important but often underappreciated player in the Earth's interdependent systems is soil. Soil plays a crucial role in the lives of the plants, animals, and other organisms that live in the biosphere and act as an essential link between the abiotic, the non-living components of the world, and the biotic, that's right, the living components of the world. And we'll see in the next chapter, soil also plays as an active role in the cycling of nutrients. Let's take a moment to review the major characteristics of soil that you'll be expected to know for the rest of the test. Soil is more than just dirt. Although we may be tempted to think of soil as simply dirt, soil is actually a complex ancient material teeming with living organisms. Some soil is hundreds of years old. In just 1 gram of soil, there may be as many as 50,000 protozoa, as well as bacteria, algae, fungi, and larger organisms such as earthworms and nematodes. About 1/2 of the volume of soil is made up of mineral materials, and about 5% is organic matter, both living and dead. The pores between the grains of minerals in soil are filled with air or water, and as a rule, the size of the particles that make up the soil determines the size of the pores between the soil particles. Soils can be categorized based on numerous physical and chemical features, including color and texture. The United States Department of Agriculture divides soil textures into 3 large groups. The categories with the smallest particle is clay, which has particles that are less than 0.002 millimeters in diameter. The next largest is silt, with particles 0.002 to 0.05 millimeters in diameter, and sand is the coarsest of soil, with particles 0.05 to 2 millimeters in diameter. Sand particles are too large to easily stick together, and sandy soils have larger pores, which means that they can hold more water. Clay easily adheres to each other, and there's little room between particles for water. Clay soil is extremely compact. Another very important characteristic of soil types is soil acidity or alkalinity. Recall that the pH of a substance ranges from 0 to 14 and is the measure of the concentration of hydrogen ions. Most soils fall into a pH range of about 4 to 8, meaning that most soils range in pH from being neutral to slightly acidic. Soil pH is important because it affects the solubility of nutrients, and this in turn determines the extent to which these nutrients are available for absorption by plant roots. If the soil in the region is too acidic or basic, certain soil nutrients will not be able to be used by the regional plants. One last thing about soil is that the College Board wants you to know. When the pH of the soil gets more acidic, ions of heavy metals such as mercury, Hg, or aluminum, Ai, or Al, can leach into the groundwater. These ions can travel to streams and rivers and harm both plants and aquatic life. For example, aluminum ions can damage the gills of fish and cause them to suffocate. Where does soil come from? Basically, soil is a combination of organic material and rock that has been broken down by chemical and biological weathering. Therefore, it should not be surprising to learn that the types of minerals found in soil in a particular region will depend on the identity of the base rock of that region. Water, wind, and living organisms are all prominent agents of weathering, and all weathering processes are placed into the following three rather broad categories, which you should definitely know for exam day. Physical weathering, also known as mechanical weathering, any process that breaks rocks down into smaller pieces without changing the chemistry of the rock. The forces responsible for physical weathering are typically wind and water. Chemical weathering occurs as a result of chemical interactions between the water and other atmospheric gases and the bedrock of the region. One example of chemical weathering is rust, which forms when iron and other metallic elements come in contact with water. Biological weathering that takes place as the result of the activities of living organisms, such as tree roots growing and expanding through rocks. Soil is made up of distinct layers with very different characteristics. Let's discuss those next. Soil layers. Soil comprises distinct layers known as horizons, which vary considerably in content. horizon is the uppermost horizon of soil. It is primarily made up of organic materials, including waste from organisms, the bodies of decomposing organisms, and live organisms. The dark, crumbly material that results from the decomposition of organic material forms humus. A-horizon. The horizon below the O-horizon is called the A-horizon, and this layer is made up of weathered rock and some organic material that has traveled down from the O layer. The A layer is often referred to as topsoil and plays an important role in plant growth. This is the zone of leaching. E-horizon, in between the A and B horizon. The E-horizon, or elevated horizon, is one that has been leached of clay, iron, or aluminum oxides. Minerals in this layer are sand and silt size. B horizon. This layer lies below the A horizon. The B layer receives all of the minerals that are leached out of the A horizon, as well as organic materials that are washed down from the topsoil. This is the zone of elevation. Elevation is a movement of dissolved material from higher soil layers to lower soil layers due to downward movement of water, which is caused by gravity. Sea horizon. The bottommost layer of soil is the sea horizon. The sea horizon is composed of larger pieces of rock that have not undergone much weathering. The bedrock, which lies below all of the other layers, is referred to as the R horizon. Soil problems for and caused by humans. In order to be able to grow all the foods that humans consume, we must have enough arable or suitable for plant growth soil to meet our agricultural needs. Soil fertility refers to soil's ability to provide essential nutrients like nitrogen, potassium, and phosphorus to plants. Humus, remember it's in the O layer, is an extremely important component of soil because it's rich in organic matter. Soil is composed of roughly the same amount of all three textures. Remember, clay, silt, and sand are described as being loamy, and these types of soil are considered the best for plant growth. Another important characteristic of soil for agricultural purposes is the extent to which it aggregates or clumps. The most fertile soils are aggregates of soils of different textures bound together with organic materials. Monoculture. Unfortunately, certain agricultural activities can change the texture of soil. For example, repeated plowing tends to break down soil aggregates, leaving plowpan or hardpan, which is hard, unfertile soil. Whereas communities traditionally planted many different types of crops in a field, in modern agriculture, the monoculture, or the planting of just one type of crop in a large area, predominates. Over the history of agriculture, a significant decrease in the genetic diversity of crop species has taken place. This creates numerous problems. First of all, a lack of genetic variations makes crops more susceptible to pests and diseases. Secondly, the consistent planting of one crop in an area eventually leaches the soil in that area of a specific nutrient that the plant needs in order to grow. One way to prevent this phenomenon is to practice crop rotation, in which different crops are planted in the area in each growing season. Another practice that farmers will use to increase sustainability is polyculture, planting several crops on the same plot of land simultaneously. This increases biodiversity. Other problems with modern agriculture include its reliance on large machinery, which can damage soil, and the fact that, as an industry, agriculture is a huge consumer of energy. Energy is consumed by both the production of pesticides and fertilization, and in the use of fossil fuels to run farm machinery. The past 50 years or so have seen a huge increase in the worldwide agricultural productivity, which is largely due to mechanization of farming that resulted from the Industrial Revolution. The boom in agricultural productivity is known as the Green Revolution, and unfortunately it has since had many detrimental effects on the environment. For example, the use of chemical pesticides resulted in the emergence of new variety of pesticide-resistant insects. Recently, the introduction of genetically modified plants has enabled researchers to take steps in solving the problem of pesticide-resistant insect species. Another drawback to the Green Revolution resulted from the dramatic increase in the irrigation worldwide. Over-irrigated soils undergo salinization. In salinization, the soil becomes waterlogged, and when it dries out, salt forms a layer on its surface. This eventually leads to land degradation. In order to combat this problem, researchers have developed drip irrigation, which allots an area only as much water as is necessary and delivers the water directly to the roots. Soil erosion. As you learned earlier, the small rock fragments that result from weathering may be moved to new locations in the process of erosion, and bare soil upon which no plants are growing, is more susceptible to erosion than soil that's covered by organic materials. Because one of the soil constant movement of water and wind on Earth's surface, the erosion of soil is a continual and normal process. However, when erosion removes valuable topsoil or deposits soil in undesirable places, it can become a problem for humans. Eroded topsoil usually ends up in the bodies of water, posing a problem for both farmers who need healthy soil for planting and people who rely on the bodies of water to be uncontaminated with the soil runoff. The most significant portion of erosion caused by humans resulted from logging and slash and burn agriculture, which is characterized by cutting down and burning trees to clear land for agricultural purposes. The removal of plants in an area makes the soil much more susceptible to the agents of erosion. Unfortunately, human activities such as the ones we have just discussed, the cultivation of agricultural fields, overgrazing, urbanization, and deforestation have significantly increased the levels of erosion in the upper layer of soil. These processes will continue to create problems for farmers searching for arable land until new techniques that preserve the integrity of soil are introduced and utilized. Soil conservation. In order to conserve soil resources, several best management practices have been developed. These practices return organic material to the soil, slow down the effects of wind, and reduce the amount of damage done to soil by tillage, plowing. Here are some of the more common methods. Use of animal waste, manure, compost, and the residue of plants to increase the amount of organic material in soil. Practice of organic agriculture, a method of farming that utilizes compost, manure, crop rotation, and non-chemical methods to manage soil fertility and pest control. Organic producers do not use or strictly limit the use of chemical fertilizers and pesticides or genetically modified organisms. Modification of tillage practices to reduce the breakup of soil and to reduce the amount of erosion. These include counterploughing and strip planting. Use of trees and other wind barriers to reduce the force of the wind. Much of what we know about soil conservation was established relatively recently. The Soil Conservation Act was passed in 1935 and led to the creation of the Soil Conservation Services. These were created in response to the Dust Bowl of the 1930s, which was a period of unprecedented dust storms caused by severe drought and ill-advised farming practices. This program was created to conserve soil and restore the nation's ecological balance and was led by soil conservation pioneer Hugh Hammond Bennett. Soil laws. The federal government recognized the need to protect the vital resource. Review the first two laws below that relate to preserving soil. 1977 Soil and Water Conservation Act. This act established soil and water conservation programs to aid landowners and users. It also set up conditions to continue evaluating the conditions of U.S. soil, water, and related resources. 1985 Food Security Act. Nicknamed the Swamp Buster, this act discouraged the conversion of wetlands to non-wetlands. In 1990, federal legislation denied federal farm supplements to those who converted wetlands to agriculture and provided restoration of benefits to those who converted lands to wetlands. Phew, got it? You're almost at the halfway point of this chapter. If you want, go get a glass of water or a snack to bolster you for the remaining pages. I will be right back. And we are back. Now we will turn to a study of what surrounds Earth, the atmosphere. The atmosphere. In the broadest definition, the atmosphere is a layer of gases that held close to Earth by the force of gravity. The layer of gases that lie closest to Earth is the troposphere. It extends from Earth's surface to about 10 to 20 kilometers or 5 to 10 miles. The troposphere is where all the weather that we experience takes place. This layer contains the majority of atmospheric water vapor and clouds. And generally, the troposphere is vertically well mixed, and with the exception of periods of temperature inversions, it gradually becomes colder with an increase in altitude by about 6.5 degrees Celsius a kilometer. You've probably heard about the troposphere before in the news because of the greenhouse effect. The troposphere contains certain gases called greenhouse gases, the most important of which are H2O and CO2. As the sun's rays strike Earth, some of the solar radiation is reflected back into space. However, greenhouse gases in the troposphere intercept and absorb a lot of this radiation. We'll further investigate the greenhouse effect in Chapter 9, but for now, take a look at the following figure. Crowning the troposphere is the tropopause, which is a layer that acts as a buffer between the troposphere and the next layer up, the stratosphere. In this buffer zone, the atmospheric temperature is no longer decreases with altitude. Instead, the temperature begins to increase with altitude. The stratosphere sits on top of the tropopause and extends about 20 to 50 kilometers above Earth's surface. Unlike the troposphere, its gases are not very well mixed, and as in the tropopause, the temperature in the stratosphere increases as the distance from Earth increases. This warming effect is due to a thin band of ozone, O3, that exists in this layer. The ozone traps the high-energy radiation of the sun, holding some of the heat and protecting the tropopause and Earth's surface from this radiation. Above the stratosphere are two layers called the mesosphere and the thermosphere, ionosphere. The mesosphere extends about 80 kilometers above Earth's surface and is the area where meteors usually burn up. The thermosphere is the thinnest gas layer. It is located about 110 kilometers above Earth and is where auroras takes place. It's also the layer of the atmosphere where space shuttles orbit. The thermosphere is also known as the ionosphere because of the ionization that takes place in this region. This region also absorbs most of the energetic charged particles, such as protons and electrons, solar winds from the sun. Interestingly, the thermosphere also reflects radio waves, which is what makes long-distance radio communication possible. You'll need to know how the climates that we experience on Earth are created by the atmosphere. So let's go into this next. Climate. Earth's atmosphere has physical features that change day to day as well as patterns that are consistent over a space of many years. The day-to-day properties such as wind speed and direction, temperature, amount of sunlight, pressure, and humidity also referred to as weather. The patterns that are constant over many years, 30 years or more, are referred to as climate. The two most important factors in describing climate are average temperature and the average precipitation amounts. Meteorologists are scientists who study weather and climate. The weather and climate of any given area is the result of the sun unequally warming and the gases above it, as well as Earth's rotation. Air circulation in the atmosphere. The motion of air around the globe is the result of solar heating, the rotation of Earth, and the physical properties of air, water, and land. There are three major reasons why Earth is unevenly heated. More of the sun's rays strike the Earth at the equator in each unit of surface area then strike the poles in the same unit area. The tilt of Earth's axis points regions toward or away from the sun. When pointed toward the sun, those areas receive more direct or intense light than when pointed away. This causes the seasons we experience. Earth's surface at the equator is moving faster than at the poles. This changes the motion of air into major prevailing winds, belts of air that distribute heat and moisture unevenly. Winds moving north from the equator in the northern hemisphere are deflected to the right or east, and winds moving south from the equator in the southern hemisphere are deflected to the left or west. This deflection is known as the Coriolis effect. Solar energy warms Earth's surface. The heat is transferred to the atmosphere by radiation heating. The warmed gases expand, become less dense, and rise, creating vertical currents called convection currents. The warm currents can also hold a lot of moisture compared to the surrounding air. As these large masses of warm, moist air rise, cool air flows along Earth's surface into the area where the warm air was located. This flowing air or horizontal airflow is one way that surface winds are created. As warm, moist air rises into the cooler atmosphere, it cools to the dew point, the temperature at which water vapor condenses into liquid water. This condensation creates clouds. If condensation continues and the water drops get bigger, they can no longer be held up by the convection in Earth's atmosphere and they fall as precipitation, which can be frozen or liquid. The cold, dry air is now denser than the surrounding air. This air mass then sinks to Earth's surface, which is where it is warmed and can gather more moisture, thus starting the convection cell rotation again. On a local level, this phenomenon accounts for land and sea breezes. On a global scale, these cells are called Hadley cells. A large Hadley cell starts its cycle over the equator, where the warm, moist air evaporates and rises in the atmosphere. The precipitation in that region is one cause of the abundant equatorial rainforest. The cool, dry air then descends around about 30 degrees north and south of the equator, forming the belts of deserts seen around the Earth at those latitudes. Seasons: the motion of Earth around the Sun and Earth's axial tilt of 23.5 degrees together create the seasons that we experience on Earth. This results in variation in the insolation, the amount of solar radiation that reaches a given region or different parts of the Earth with the time of the year. When Earth is in part of its orbit in which the northern hemisphere is tilted toward the sun, the northern half of the planet receives more direct sunlight for longer periods of time each day than does the southern hemisphere. This means that when the northern hemisphere is experiencing summer, the southern hemisphere is experiencing winter. Interestingly, because of the Earth's tilt, the sun rises and sets just once a year at the north and south poles. Approximately 6 months of the year at the poles are daytime, while the other 6 months are dark and considered nighttime. Albedo reflectance. Another important property that affects the climate of different regions on the Earth is albedo, the percentage of insolation that reflected by a surface. The lower the surface albedo, the more solar radiation that is absorbed. An albedo value of 0 corresponds to 0 reflectance and absorption of all radiation, whereas an albedo value of 1 corresponds to reflection of all incoming radiation. Snow and ice have high albedo rates, while land and trees have lower albedo rates. Changes in the albedo can lead to alterations in temperatures. For example, snowfall may raise the albedo of an area, leading to an increase in the reflection of solar radiation and a decrease in the temperature. Let's move on to discuss winds. You might be thinking, I know what wind is, so I can skip this section. Don't skip it. The AP Environmental Science exam may ask you about the specific types of winds and air movements coming up next, so it's better to be safe than sorry. Types of winds. So what is wind? Why does everyone refer to wind when they're discussing weather? Well, the term wind is widely used to refer to air currents, and we already know that air currents tend to flow from regions of high pressure to regions of low pressure. But let's review some important details you'll need to know about wind before we move on to our review of the hydrosphere. Formally speaking, wind is air that's moving as a result of the unequal heating of Earth's atmosphere. It is part of Earth's circulatory system and moves heat, moisture, soil, and even pollution around the planet. One crucial wind-related phenomenon that you'll need to know about for the AP Environmental Science exam is trade winds. Trade winds were named for their ability to quickly propel trading ships across the ocean. The trade winds that blow between about 30 degrees latitude and the equator are steady and strong and travel at a speed of about 11 to 13 miles per hour. In the northern hemisphere, the trade winds blow from the northeast and are known as the northeast trade winds. In the southern hemisphere, the winds are blown from the southeast and are called the southeast trade winds. Another important type of moving air mass called a westerly travels south and west in the northern hemisphere, north and west in the southern hemisphere near the equator between 30 and 60 degrees. The movement of air that accounts for the westerly, called the Furrow cell, is the reverse of the Hadley cell. Westerlies are another result of the Coriolis effect. Polar easterlies are formed by similar forces. In polar easterlies, winds between latitudes 60 degrees and the North Pole blow from the north and east, and winds between 60 degrees and the South Pole blow from the south and east. Between the wind belts mentioned above, air movement is less predictable and often no winds blow at all for days. For example, between about 30 to 35 degrees north and 30 to 35 degrees south of the equator lies the region known as horse latitudes, or the subtropical high. Subsiding dry air and high pressure result in very weak winds in this region. Some people say that sailors gave the region of the subtropical high the name horse latitude because ships relying on wind were unable to sail in these areas. Afraid of running out of food and water, sailors threw their horses and other live cargo overboard to save on food and water, and to make the ship lighter and easier to move. Similarly, the air near the equator is relatively still because air at these locations is constantly rising and not blowing. For this reason, early sailors called this region the doldrums. The doldrums, which exist between 5 degrees north and 5 degrees south of the equator, are also known as the Intertropical Convergence Zone, or ITCZ for short. The trade winds converge in the area of the ITCZ, producing convectional storms that produce regions with some of the world's heaviest precipitation. The last type of moving air that you'll need to be familiar with for the exam is a jet stream. Jet streams are high-speed currents of winds that occur in the uppermost troposphere. These fast-moving air currents have a large influence on local weather patterns. Got it? Let's move on to review the types of weather that result from all of these moving air masses. Weather events. Let's start by discussing the monsoon. Monsoons, or seasonal winds that are usually accompanied by very heavy rainfall, occur when land heats up and cools down more quickly than water does. In a monsoon, hot air rises from the heated land and a low pressure system is created. The rising air is quickly replaced by cooler moisture that blows in from over the sea. As the air rises, it cools, and the moisture carries is released in a steady seasonal rainfall. This process happens in reverse in the dry season, when masses of air that have cooled over the land blow out over the sea or ocean. Monsoons primarily occur in the coastal areas. Check out this helpful illustration. On a smaller scale, this effect can be seen on the shores of large lakes or bays. In these areas, again, the land warms faster than does the water during the day, so the air mass over the land rises. Aside from air from over the lake moves in to replace it, and this creates a breeze. At night, the reverse happens. The land cools more quickly than the water, and the air over the lake rises. The air mass from the land moves out over the sea to replace the rising air, and this creates a breeze as well. If you live in Chicago or San Francisco, you may have experienced this small-scale monsoon effect. As we mentioned above, the air that moves in from over the ocean or large bodies of water contains large amounts of water. If an air mass is forced to climb in altitude, if, for instance, it encounters an obstruction such as a mountain, the air will be forced to rise. When the air mass rises, it will cool and water will precipitate out on the ocean side of the mountain. By the time the air mass reaches the opposite side of the mountain, it will be virtually devoid of moisture. This phenomenon is known as the rain shadow effect and is responsible for the impressive growth of the Olympic rainforest within Olympic National Park on the Washington state coast. Interestingly, Olympic National Park has a temperate rainforest on its west side where annual precipitation is about 150 inches, making it perhaps the wettest area in the continental United States, and forces on its much drier east side, whose annual precipitation is around 15 inches. Remember, trade winds from the last section, well, they occur in steady and somewhat predictable wind patterns, but they may cause local disturbances when they blow over very warm ocean water. When this occurs, the air warms and forms an intense, isolated low-pressure system while also picking up more water vapor from the ocean surface. The wind will circle around this isolated low-pressure air area counterclockwise in the northern hemisphere and opposite in the southern hemisphere. Once again, because of the Coriolis effect, the low-pressure system will continue to move over warm water, increasing in strength and wind speed. This will eventually result in a tropical storm. Certain tropical storms are of sufficient intensity to be classified as hurricanes. Hurricanes have winds with speeds in excess of 130 kilometers an hour. The rotating winds of a hurricane remove water vapor from the ocean's surface, and heat is released as the water vapor condenses. This addition of heat energy continues to contribute to the increase in wind speed, and some hurricanes have winds traveling at speeds of nearly 400 kilometers per hour. A major hurricane contains more energy than that released during a nuclear explosion, but since the force is released more slowly, the damage is generally less concentrated. Another important note about this type of storm is that they are referred to as hurricanes in the Atlantic Ocean, but they are called typhoons or cyclones when they occur in the Pacific Ocean. Go figure. El Niño is a climate variation that takes place in the tropical Pacific about once every 3 to 7 years, and it lasts for about 1 year. Under normal weather conditions, trade winds move the warm surface water of the Pacific away from the west coast of Central and South America. As a result, the cold ocean water that lies under the displaced water moves to the surface, causing the thermocline or line of demarcation between two layers of water in the freshwater biome to rise, bringing nutrients with it and keeping the temperatures of the coastal water relatively cool. This phenomenon is called upwelling. During El Niño, the normal trade winds are weakened or reversed because of the reversal of the high and low pressure regions on either side of the tropical Pacific. This reversal of pressure systems is known as the Southern Oscillation. Without these regular trade winds off the Central and South American coast, the process of upwelling slows or stops, and the water off the coast becomes warmer and contains fewer nutrients. This means that during El Niño, the northern United States and Canada experience warmer winters and a less intense hurricane season. The eastern United States and regions of Peru that are typically drier have higher than average rainfall, and the Philippines, Indonesia, and Australia are drier than normal. One environmentally important effect that El Niño has on humans is that because of the suppression of upwelling, the offshore fish population of certain coastal areas decline. In countries like Peru, which rely heavily on fishing, El Niño has devastating economic effects. The reverse of El Niño is known as La Nina. The Coriolis effect contributes to La Nina conditions. As air moves toward the equator to replace rising hot air, the moving air deflects to the west and helps move the surface water, allowing the upwelling. During La Nina, the surface water of the ocean surrounding Central and South America are colder than normal. Finally, the alterations of atmospheric conditions that led to El Niño and La Nina are referred to as ENSO events. This stands for El Niño and Southern Oscillation. The hydrosphere. Water covers about 75% of the planet Earth. Most of the water on Earth's surface is salt water. On average, the salt water in the world's ocean has a salinity of about 3.5%. This means that for every 1 liter of seawater, there are 35 grams of salt, mostly but not entirely sodium chloride dissolved in it. In fact, 1 cubic foot of seawater would evaporate to leave about 2 pounds of sea salt. However, seawater is not uniformly saline throughout the world. The planet's freshest seawater is in the Gulf of Finland, part of the Baltic Sea. The most saline open sea is the Red Sea, where high temperatures and confined circulation result in high rates of surface evaporation. Fresh water is water that contains only minimal quantities of dissolved salt, especially sodium chloride. All fresh water ultimately comes from precipitation of atmospheric water vapor, which reaches inland lakes, rivers, and groundwater bodies directly or after melting of snow or ice. Let's start a discussion of fresh water before discussing the world's oceans. We will end this section with a review of the ways in which humans use water, global problems associated with water usage, and issues of water conservation. Fresh water. Fresh water is deposited on the surface of the earth through precipitation. Water that falls on the earth and doesn't move through the soil to become groundwater moves along Earth's surface via gravity, forms small streams, and then eventually forms larger ones. The size of the streams will continue to increase as the water is added to it until the stream becomes a river, and the river will flow until it reaches the ocean. This land area that drains into a particular stream is known as a watershed or drainage basin. As water moves into the stream, it carries with it sediment and other dissolved substances, including small amounts of oxygen. Turbulent waters are especially laden with dissolved oxygen and carbon dioxide, such as those found at the source or headwaters of a stream. As a general rule, the more turbulent the water, the more dissolved gases it will contain. As you probably know, fresh water that travels on land is largely responsible for shaping Earth's surface. Erosion occurs when the movement of water etches channels into rocks. The moving water then carries eroded material farther downstream. Because of the obstructions on land, moving water does not move in a straight line. Instead, it follows the lowest topographical path, and as it flows, it cuts farther into its banks to eventually form a curving channel. As the water travels around these bends, its velocity decreases and the stream drops some of its sedimentary load. Water always follows the path of least resistance as it travels from the highlands to the sea. Rivers drop most of their sedimentary load as they meet the ocean because their velocity decreases significantly at this juncture. And at these locations, landforms called deltas, which are made of deposited sediments, are created. Another important freshwater body that you should know about is the estuary. Estuaries are sites where the arm of the sea extends inland to meet the mouth of the river. Estuaries are often rich with many different types of plants and animal species because the fresh water in these areas usually have a high concentration of nutrients and sediments. The waters in estuaries are usually quite shallow, which means the water is fairly warm, and the plants and animals in these locations can receive a significant amount of sunlight. Some subcategories of estuarine environments that you should know for the exam are saltwater marshes, mangrove forests, inlets, bays, and river mouths. Some of the Earth's most important ecologically diverse ecosystems are the areas along the shore of fresh bodies of water known as wetlands. Types of wetlands include marshes, swamps, bogs, prairie, potholes, which exist seasonally, and the floodplains, which occur when excess water flows out of the bank of a river and into a flat valley. So those are the main types of freshwater bodies you'll need to know. Let's review the stratification of freshwater bodies, get through oceans, and move on. The fun stuff, the impacts of water use on humans. Vertical stratification and freshwater biomes. In all natural bodies of water, there exist layers of water that vary significantly in their temperature, oxygen content, and nutrient levels. These layers are affected differently by seasonal changes and other disturbances, and this also contributes to how they are categorized. In freshwater, the layers are the epilymnion, which is the uppermost and thus the most oxygenated layer, and the hypolimnion, which is the lower, colder, and denser layer. The demarcation line between these two layers, at which the temperature shifts dramatically, is the thermocline. These layers are also often delineated based on what types of organisms that can live in them. You should definitely be familiar with the following term for the AP Environmental Science test, so take note. Littoral zone begins with the very shallow water at the shoreline. Plants and animals that reside in the littoral zone receive abundant sunlight. The end of the zone is defined as the depth at which rooted plants stop growing. Limnetic zone, surface of open water, the region that extends to depths that sunlight can penetrate. Organisms that reside in this region are short-lived and rely on sunlight to carry out photosynthesis. Profundal zone, water that is too deep for sunlight to penetrate because the profundal zone is a photic zone, a zone that light cannot reach. Photosynthesizing plants or animals cannot live in this region. Benthic zone, the deepest layer in the body of water, characterized by very low temperatures and low oxygen levels. The world's oceans. Before we get into our review of the world's oceans, let's consider another aquatic system besides wetlands and estuaries. That's an important source of biodiversity. This one is a saltwater ecosystem. Certain landforms that lie off coastal shores are known as barrier islands. Because barrier islands are created by the buildup of deposited sediments, their boundaries are constantly shifting as water moves around them. These spits of land are generally the first hit by offshore storms, and they are important buffers from the shoreline behind them. In tropical waters, a very particular type of barrier island called a coral reef is quite common. These barrier islands are formed not from the deposition of sediments, but from a community of living things. These organisms responsible for the creation of coral reefs are cnidarians, which secrete a hard calciferous shell. These shells provide homes and shelters for incredible diversity of species, but they are also extremely delicate and thus very vulnerable to physical stress. Changes in light intensity, changes in water temperature, and ocean depth and pH. The increase in ocean temperature and dissolved CO2 due to climate change is resulting in coral bleaching. The coral release the colorful algae which provide them with food. Like freshwater bodies, oceans are divided into zones based on changes in light and temperatures. They're listed below again and again. Knows I'm cold for the test. Coastal zone. This zone consists of the ocean water closest to land. Usually it is defined as being between the shore and the end of the continental shelf. Euphotic zone, the photic upper layer of water. The euphotic zone is the warmest region of water. This zone also has the highest level of dissolved oxygen. Bestial zone, the middle zone. The zone receives insufficient light for photosynthesis and is colder than the euphotic zone. Abyssal zone, this is the deepest region of the ocean. This zone is marked by extremely cold temperatures and very low levels of dissolved oxygen, but very high levels of nutrients because of the decaying plant and animal matter that sinks down from the zones above. Both freshwater and saltwater bodies experience a seasonal movement of water from the cold and nutrient-rich bottom to the surface. These upwellings provide a new nutrient supply for the growth of living organisms in the photic region. Therefore, they are followed by an almost immediate exponential growth in the population of organisms in these zones, especially the single-cell algae, which may form blooms of color called algal blooms. These algae can also produce toxins that may kill fish and poison the beds of filter feeders, such as oysters and mussels. One notorious recurring toxic algal bloom is referred to as red tide. This is caused by a proliferation of dinoflagellates. Water is densest at 4 degrees Celsius in non-tropical regions of the Earth. After spring ice melt, the water surface temperature of lakes and ponds will rise from 0 degrees Celsius to 4 degrees Celsius, whereupon this dense surface water will sink to the bottom of the lake or pond. This will displace water at the bottom of the lake or pond to the surface. This over turn brings oxygen to the bottom and nutrients to the top of the lake or pond, and occurs during spring and fall as the temperatures of the ecosystems change from cold to warm or the reverse. Ocean currents. Ocean currents play a major role in modifying conditions around the Earth that can affect where certain climates are located. As the sun warms the water in the equatorial regions of the globe, prevailing winds, differences in salinity, saltiness, and Earth's rotation set ocean water in motion. For example, in the northern hemisphere, the Gulf Stream carries sun water along the east coast of the United States and as far as Great Britain. This warm water displaces the cold, denser water in the polar region, which can move south to be rewarmed by the equatorial sun. Northern Europe is kept 5 degrees Celsius, 10 degrees Celsius warmer than it would be were the current not present. Oceanographers also study a major current, the ocean conveyor belt, that moves cold water in the depth of the Pacific Ocean while creating a major upwelling in other areas of the Pacific. Water, everything and not. As you know, we all need water in order to live. In particular, communities need water for many different industries, including fisheries, recreation, transportation, and agriculture. Agriculture is one of the biggest water users of all time. About 73% of the global demand for water is for crop irrigation. Industry accounts for about 21% of all water use, and domestic use accounts for about 6%. Since the 1950s, global water use has tripled, mostly due to population growth and improvements in the global standard of living. One way that humans have recently dealt with potential water shortages in communities is through interbasin transport. During the interbasin transport, water is transported very long distances from its source through aquifers or pipelines. An example of this type of engineering is the pipeline that now exists between the western and eastern slopes of the Rocky Mountains in Colorado, known as the Big Thompson Project. 213,000 acre-feet of water are delivered annually to the eastern slope of Colorado. However, this method has several negative effects. It can result in different geographic areas arguing over water rights. It can also have serious environmental repercussions. Interbasin transfers can increase the salinity of the water and even change the climate of an ecosystem. In North America, especially, humans rely on groundwater as a primary source of water for everyday use. Groundwater refers to any water that comes from below the ground, that is, from wells or aquifers, which are underground beds or layers of earth, gravel, or porous stone that yield water. Water found in an unconfined aquifer is free to flow both vertically and horizontally. A confined aquifer, however, has boundaries that don't readily transport water. Our reliance on and use of groundwater has several detrimental environmental effects. For example, it can result in a depressed water table and the drying of local groundwater sources. In the late 1990s, a drought in Florida resulted in such a severe reduction in the aquifers that roads collapsed from the lack of structural support. Subsidies of Earth's surface is another serious consequence of groundwater. Additionally, aquifers can be compacted, meaning that the mineral grains collapse on each other and the area is unable to hold as much water. In some urban areas, humans have rendered the groundwater incapable of being replenished by building structures and roads that are impermeable to precipitation. Global water needs. Scientists differentiate between countries that are water stressed and those that are water scarce. Countries that are water stressed have a renewable annual water supply of about 1,000 to 2,000 meters cubed per person, but countries that are water scarce have less than 1,000 meters cubed per person. Many of the countries that are currently considered water scarce are developing countries that have rapidly increasing populations, which means that their water scarcity problems will grow over time. Some of the water scarce countries that exist today are Algeria, Egypt, Libya, Kenya, Rwanda, Tunisia, Israel, Jordan, Kuwait, Saudi Arabia, Syria, Belgium, Hungary, the Netherlands, Singapore, Barbados, Malta, Lebanon, Morocco, Niger, Somalia, South Africa, and Sudan. Clearly, that's a lot of countries. Unfortunately, many more are expected to be water scarce by the year 2050. Water use in the United States. The United States is not considered water scarce, but certain regions of the United States are considered water stressed. Additionally, water use in the United States is out of control. We use water more quickly than is possible to be replenished. So water scarcity is definitely in our future if we continue to use water at our present furious rate. The hydraulic cycle supplies the water that we use for all of our activities. Water used in our homes, manufacturing, cooling equipment that generates electricity, and irrigating croplands are a few examples. To give you a sense of water use in the United States, take a long look at the chart that shows trends in the water withdrawal and populations from 1950 to 2010. As you can see, the nation's water use peaked in about 1980 and has been fairly steady since then. Many of the stresses for our greater water use has risen since 1980, such as population irrigation of crops to feed this larger population and more industry, yet total water use has not risen. This shows that water conservation efforts and greater efficiencies in using water have had a positive effect in the last 35 years. Nonetheless, we often hear environmental news stories covering droughts, proposed emergency water relief plans, and rules about lawn watering. What are we doing about it? Water is a tricky business. It is difficult for politicians and lawmakers to put restrictions on water use because many people think that water should be free. After all, it falls from the sky. We can take a bucket from the lake down to the street and no one will arrest us for stealing. For the AP Environmental Science exam, you should know about certain concepts of human water rights. The first is the idea of riparian rights. Riparian means of, on, or relating to the banks of a natural course of water. and riparian right is the right of people who have legal rights to use that area. Alternatively, in prior appropriation, water rights are given to those who have historically used the water in a certain area. In other words, prior appropriation can be thought of as a water squatter's right. It had been proposed that in order to solve current global water crises, we simply take the tons of ocean water and desalinate it. This is a fairly simple process physically, but unfortunately it isn't economically viable because it takes a great deal of energy to remove the salt through distillation or reverse osmosis. As water becomes scarcer globally, it will become important for countries to think about ways to regulate the use of water. That's everything you'll be expected to know for the exam about water, and you're done with your studying of Earth's interdependent systems. Answer the questions in the drills found on the next few pages, and then move on to the next chapter. The end.